All right, so the meeting is now recorded. So we can start. Hello, everyone. Welcome to episode 70 of the Warsaw Quantum Computing Group meetups. My name is Pavel. I'll be the host today and the moderator. And it's my pleasure to host two great speakers from Romania, our guests. So we have Radu Marginean and we have Sorin Bos. So they will give a talk about two new tools for quantum computing. So Radu will start and then Sorin will follow. Before we proceed, just a few announcements. So as you can see, this meeting is recorded. So hopefully the video will be later available on our YouTube channel. There will be a Q&A session at the end, but if you have any questions, feel free to post your questions on the chat. And if there is an opportunity, we can try to interrupt and ask some questions on the fly, but there will be a dedicated Q&A session at the end. We would like to thank our strategic partners for supporting us and making this event, these meetups, webinars possible. Sonovero R&D, Quantum.io, Onyx, Cogit, AIQ Lab, and FinQubit. We would also like to thank our honorary partners who help us in advertising these events. And I think we can proceed. So I will now stop sharing my screen. And Radu, you can try to share your screen again. Okay, you can enable the full screen mode. And Sorin, I think it should be possible for you to share your screen later too. So I think we can start. Radu, the Zoom is yours. Enjoy the session.
Okay, thank you. I will start with a short motivation on why we have created these two tools. And I will start with a few things that almost nobody tells you about quantum computing. So first of all, the experimental dissociation energy for a hydrogen molecule is about 0.164 Hartree. And for this, you can infer the correct electronic energy for hydrogen to be about 1.174 Hartree. Now, the electronic energy of the hydrogen molecule measured with VQE using STO3G, which is the minimum orbital basis, is 1.137, which is quite different from 1.174. Now, this value, 1.137, is actually the FCI result. So this is the chemical accurate result when it's calculated in the minimum orbital basis. So as you know, the Hilbert space has infinite dimension. But when you do a calculation on a molecule, you need to work in a space of finite dimension, and you select a set of orbitals. STO3G is the minimum set of orbitals, and for this, the inferred and FCI result, which is equal to the results that you get using VQE, it's very good, but it's quite far from the accurate experimental result. Now, of course, you can run VQE using a larger orbital basis. And when you do that, you get values which get even closer to the actual result with an accuracy which is comparable with the chemical accuracy. So chemical accuracy is basically the gold standard for quantum chemistry. If you have a result which is precise within chemical accuracy, then in general, you can say you have a very good result and a useful one. Now, this discussion does not take into account the noise, which is inherent in all real quantum devices. So the results that I showed you were obtained using ideal simulators. And when you take noise into account using the current devices, the impact of noise is comparable in a size with the chemical accuracy. So just to remember, so it's about 0.0016 Hartree, which is the chemical accuracy, and this is similar with the impact of the noise for the VQE calculation on hydrogen molecule. But the result I showed you, the experimental dissociation energy is far more precise, and actually a very careful quantum mechanical calculation of this value can reproduce the experimental result very, very well within the experimental limits. So as you see, the results obtained using VQE and using just a few orbitals or even some larger orbitals is quite far from a very precise results that you would get using conventional quantum mechanical calculations. So it is often said that quantum computers will begin to be useful in chemistry for systems with 40 orbitals or more. Now, if the question is, if such difficulties exist for simplest molecule like hydrogen, will 40 qubits be sufficient to simulate anything of practical interest? And actually, probably the answer is no. So even if you would target a medium-sized molecule that you would like to simulate using VQE, and if this molecule in the minimal basis may have 40 orbitals or around 40 orbitals, if you actually want a good result, an accurate result, you will need much more orbitals than that. Another blocking issue for hybrid algorithms are the barren plateaus. These are exponentially vanishing gradients in an optimization energy landscape. The existence of barren plateaus has been established, and it's not a contentious issue, but the practical impact of various mitigation strategies and the practical impact on VQE remain unclear, at least for the moment. Another problem, which is not a secret, but which tends to be omitted, is the fact that VQE simply does not scale, especially on molecules. So the problem is not the number of qubits, because we already have quantum devices with more than 1,000 qubits. The problem is the number of shots that you need to take, which grows very fast. There are hundreds of papers that investigate methods to speed up VQE, but if you are looking for actual implementation, you will find just a few of those. Another issue is that many software tools are research grade, not production grade. Just to explain what I mean by that, you should try to pick up a medium-sized molecule and do not even try to run VQE, just set up your code in order to prepare all your Python objects to run VQE on a system with about 20 orbitals. Basically, you will see spikes in memory processing, in time needed to build up these projects. This actually on my computer, on my Jupyter notebook, the tab basically died. So and this is true for many other software frameworks. They are very good for experimental and for small or medium-sized jobs, but they are not yet up to the standards required for production in order to obtain useful, interesting results. Another issue is that while quantum computers advance year by year, classical simulation methods are also getting better as well. Advances in classical algorithms, in simulators like tensor networks, GPU optimization, problem-specific reduction push back the practical need for large quantum machines for certain problem classes. Finally, I would say that if we had a quantum computer right now with millions of qubits and perhaps 2,000 logical qubits today, we wouldn't know what to do that. What practical things would do that except for breaking RSA. And why do I say that? It's, well, I mean, Grover will, we all know Grover provides a square root of n speed up. But actually, in order to take advantage of this, you need QRAM, a device which doesn't exist. Also, implementing the Oracle itself can also nullify the square root of n speed up. This is another issue. In quantum machine learning, HHL, it's an algorithm which has in theory experimental speed up, exponential speed up, but has similar issues due to the input bandwidths. Now, I'm not saying these are not useful, and this both HHL and Grover could be used as subroutines that receive input data as a quantum state, and then you can certainly use them, and you can take advantage of the speed ups that they provide. But eventually, what we are doing it's just postponing the problem, because at some point you need to input your data, and this is you cannot, at this moment, there are no quantum repeaters. You cannot input quantum data in a quantum computer. You cannot input only classical data, and the bandwidth for inputting classical data, it's not very large. Another application would be QAOA, but QAOA with about 20,000 variables will not outperform the state of the art of classical optimization like Groby right now. Then there is quantum phase estimation. This is an algorithm which seems like a good candidate on systems with error correction. But here are problems as well. I mean, in order to run quantum phase estimation, you need to provide an input state, which should have an overlap with the state you are looking for, the ground state, which is something that you generally want to calculate. You need to provide the input state which has a significant overlap with the ground state. And for small or medium molecules, the Hartree-Fock state is a good way to do that. But for larger molecules of interest, it's unclear if the Hartree-Fock state, which can be easily calculated, has actually a significant overlap in order to perform quantum phase estimation algorithm. Now, I'm not saying that quantum advantage will not be achieved in the next few years. I mean, we've seen a promising paper from IBM last year and from D-Wave this year on simulating properties of spin systems. And if you talk with some people from IBM, they will tell you that in perhaps 2026, they will achieve quantum advantage on a problem of practical interest. I do not know how they will do that, but probably they will simulate some spin systems which can be done, and which does not scale as bad, even if you run VQ, it does not scale as bad as a molecule do. So one conclusion that I would draw personally is that we need more experimentation in quantum computing. And what we do here is we recognize this need, and we have created our platform in order to make exploration and experimentation easier. Okay, so I'll stop sharing these slides for the moment. That's the one. Figure out where is the, okay. Okay, so as I said, we would like to present you two tools for quantum computing. One is an IDE for quantum computing, and Sorin will be talking about this. The second is a platform. We call it Quantum Flows. You can find it on our webpage. If you go to our webpage, we can find a link to both of them. And I will just click off the try beta link, and we'll get to the platform. Now, the first thing that you need to do if you want to use our platform is obviously you need to sign in our platform, and in order to do that, you need a Google email account. Then the next thing that you would need to do is to download this Jupyter notebook, which is a demo notebook, which will let you explain you quite easily how to use our platform and what of the kinds of things that you can do. I have this notebook running here. So of course I have to import some libraries, including our own library, which we use to connect to this platform. And here we have a provider, which is nothing special. You execute this, and then we authenticate. And in order to authenticate, we use Google Auth services. So I'm using my email, and I've been authenticated. And at this moment, I can, okay, I need to this. There's a bug here, but now it will work. And then the simplest thing you can do is just run a job where you submit a simple circuit to our platform. So going back here, you can see the list of jobs. If here is a list of jobs that I have processed recently. And here is the result of for running a simple circuit. You can see the histogram. You can zoom in actually. So this is a simulation for a system with I believe it's 10 qubits. So you cannot display everything in one histogram. The bins are collapsed, but if you know what you're looking for, you can zoom in and find the actual state that you would like to find. Okay, so this is nothing very interesting. What we provide new are workflows. Workflows are prepackaged quantum computing programs that you can run, and you can do tasks in material science simulation, in quantum chemistry, in quantum machine learning, and for example, I have here a workflow for a molecule. Basically, you have on your left a list of tasks that you can use to build your workflows. All the tasks in green are input tasks. So I can provide, for example, an empty input, which is not interesting. I can provide an input molecule. I can provide an input lattice. I can provide an input optimization problem, which can be provided as a LP optimization problem in an LP format, an optimization problem using an async model, or an optimization input problem specified as a quadratic program. And then we have also machine learning tasks, which you can do. And for this, you can input data, you can input training data, you can input inference data. We have here on the right several workflows, simple workflows that you can use. So the simplest workflow is this one. It's just doing some sampling. You give it an input circuit. This is an ideal air simulator that you can use. And this would be the actual quantum mechanical task that is doing the sampling, which could be in principle a real quantum device. Now, if you are going to take a look at our backends, at this moment, we do not provide real quantum devices. We provide air simulator and a couple of fake devices from IBM. And you would probably, okay, you would be a bit disappointed, but I mean, you shouldn't be. So I will explain you why. So going back to our workflows, for example, here I have a workflow for simulating a molecule using VQE. So as I said, I have an input molecule task. Then I choose a set of orbitals that I want to use. Then I use a mapper. A mapper is it's basically a task which takes your problem Hamiltonian. The molecule has a Hamiltonian, but the quantum computer doesn't understand what it means. I mean, in order to you need to translate your Hamiltonian in a language which quantum computers understand, which is Pauli gates. So basically, you take your input molecule, you turn into a list of Pauli strings, which you can simulate on a quantum computers. And this is what the mapper is doing. Then you get, you choose your problem. In this case, it's an electronic structure problem. You can have a lattice problem, you can have an optimization problem, or you can have a QML problem. Then you choose an ansatz for your algorithm. Then you choose your algorithm for optimization. This is the classical algorithm, which is doing minimization in QAA or VQE. And this is the algorithm that you can use. At this moment, we support just VQE, simply VQE and QAA, but we'll provide others as well soon enough. So as I said, the simplest workflow is sampling. You can calculate the expectation value of an operator. You give it an input, a circuit, and an operator, and will calculate the expectation value. You can calculate the variance for an operator. Again, you give an input circuit, an input operator, and will calculate the variance. You can, of course, calculate both classically or quantum mechanically, but and you can, of course, skip this one if you want to. So for VQE, as I said, you can do a molecule VQE. You can run VQE on a lattice. You can run QA, and you can run several tasks for quantum machine learning. So you can do a quantum neural network classifier, where again, you specify some training data, some inference data, you specify a feature map, which is used to map your data in a quantum mechanical state. You specify a loss function, you specify the problem, which in this case is a quantum machine learning problem. Again, you specify an ansatz, classical algorithm for minimization. You need to specify a neural network. In this case, you will need an estimator, QNN. Then you use a neural network classifier or a neural network regressor if you have a regression problem. We also provide for kernel quantum mechanical kernel-based algorithms. And this could be simple kernels or can be trainable kernels. Okay, I will go back to our workflow jobs just to show you some results. Let's see what is the result for running a VQE calculation on a hydrogen molecule. I did not specify you, but basically when you create a workflow, you specify the program, but you do not specify the input. Here from the Jupyter notebook, you in this case, you specify a molecule, which is in this case a hydrogen molecule. And you basically, you add your molecule to your input data, then you send this task to our platform using a workflow ID, which you can copy from our platform. So each workflow has an ID, and you can use it in order to send jobs from the Jupyter Notebooks to our platform. Okay, going back to workflow jobs, I said I will show you some results for running VQE. This is some input metadata for a job. This is our input data. In this case, is an hydrogen molecule. This is the VQE result. And what you see here are various convergence values. This is the VQE value convergence. This is the minimum value, which is actually what you are looking to find out, to discover, to calculate. And these are the variances for these calculations. You can view the ansatz. You can download your circuit in OpenCASM format. You can download the circuit image if you want. You can download the parameters, which are useful because you can reuse the parameters in order to run a new calculation. So basically, our workflow, any workflow can have an input ansatz parameter, which a task, which if you select it, you can provide your ansatz as an input. And you can, assuming that you have run some VQE calculation and you have stopped at some point, you can reuse your result in order to do a subsequent calculation in order to obtain a better result. I will also show you some results for running some neural network tasks. Okay, here is our results for running a quantum neural network classifier. And you'll see here a lot of plots. We have added those plots in order to also help you get a feel of the input data, but also to get a feel of the results and what they will tell you about your problem. And also, I also here have the results for a quantum neural network regressor task algorithm. Again, you can see the results, and you can see several plots that will help you understand your result. And of course, you can download inference data. You can see here the inference data. You can see the inferred training data and inferred inference data. Of course, you can copy it and process it separately. And one last thing, you can download. There's a link at the bottom of each result page, a link towards the Qiskit code, which is used to run this. So basically, they can download the code from here, and you can then run it on a Jupyter notebook if you want to. So this is what basically our platform can do. I said I will explain you why. I mean, of course, we would like to add quantum devices, real quantum devices, to our platform, but unfortunately, running jobs on a quantum device is expensive. I mean, it's something of the order of $1 per second. So this means if you want to run a VQE for a hydrogen molecule using a minimum set of orbitals, you will need about $100 or $200. So this is very expensive. But we provide our simulators, which are free to use. And they will actually help you a lot if you want to explore the problem and understand what you can do and what cannot do with a quantum computer. Thank you very much. I think I will stop here and I will allow my colleague Sorin to continue.
Okay, thanks, Radu. Sorin, yes, you can continue.
Yeah. Just before I start, Radu, I see some people are saying that they are trying to sign up, but they are not getting the verification mail.
It's in the spam. I'm sorry. You need to change. It's in the spam folder.
They say they're not even in the spam folder.
it should be. I mean, they should.
Okay, I will try to sign up as well, and we'll see. I think Sorin, you can continue.
Okay.
No worries.
Okay, and after this, we'll provide the links for both the tools. I send the link to the quantum flows in the chat. Well, Pavel, maybe you can send an email with more information after to everybody that attended. I don't know how you guys do it.
We have a mailing list, so I can, if you can later send me all the links aggregated, and I can forward them.
Sure, great. Yeah, let me share my screen. Um, Hopefully you guys can see it. I'll just get rid of the Zoom bar.
Yes, I can see it.
Uh, yeah, so this is the other tool we wanted to show you is this coding interface, which runs entirely in the browser. You can run Python here without any backend, without any pre-installs. Basically, what we did is we run PyODide, which is a Python runtime for running in the browser, and we ported Qiskit to it, and we plan to also port Circ, Air, and other libraries, PennyLane. We want to port everything here so you can do all your coding without any Jupyter notebooks, without any backend, without any setup, without worrying about the Python version. The Qiskit version it will always be up to date. Yeah, so I've opened the interface. It took basically a couple of seconds to load all the libraries in the background. Here, because I'm signed up with GitHub, I have access to an AI assistant to the models that I have access in GitHub. So if you guys are gonna want to use this assistant, you will need to log in with your GitHub account, and then you'll have access to the GitHub models. If you have paid for more powerful models, you can access them. If not, you can access the free tier you have access in GitHub. I'm just using the free tier now. Yeah, so this is a preloaded code which just builds a Bell state. By running it, you can see the circuit, you can see the results. And now I can use here the AI assistant to just say it, help me build a 3-qubit GHZ state. Yeah, basically it shouldn't take more than a minute. I mean, more than a couple of seconds to go to query GitHub for the response. And sure enough, it came up with an explanation, but also with the code I want. So I can just copy the code from here and paste it in the code block, run it, and have the result of a GAZ state. What is also cool is that whatever circuit objects that I've built here in Python, I can also see it in the visual circuit. So I can build fairly large circuits. Of course, this is an editor that runs also in the browser. Also, this simulation is in the browser. It'll update in real time. I can also see the state vector. I can add gates in real time, and it'll update in real time, and so on. And I can see here basically all the circuit objects that are encoded in Python. I can build a second object. Let's say I just want a new circuit. Name it something else like circuit 2 with just 2 qubits, and then circuit 2. Just put a Hadamard gate on the first qubit. I can also select and only run this if I want. So it will only run the highlighted part. And if I go to the circuit, I have both the old circuit, the GAZ state, but I also have the new circuit where I only have a Hadamard gate. Yeah, basically this is pretty much where it is right now. We want to integrate backends here, but they're not, I mean, we want to integrate vendors in this platform so you can submit jobs. Right now, you can only use the simulators that are built in Qiskit. We don't have AIR, which is now a separate library, but we will pretty soon. From here, you can access the workflows, the workflow platform that Raju just showed. And of course, we really do value your feedback. We want to know if you think this is useful, what features you would like to see or you are missing, or if something doesn't work for you, please, this can be anonymous. You don't have to send your email unless you want to.
Mhm.
Yeah, that's about it from me too.
Okay, great. Thank you. Thanks, Sorin. Radu, is there
If I
something
can
you...
jump in,
Yes, yes, please. Mhm.
so I did verify, and indeed the mail is not being sent for some reason. So I'll have to look into that. I'm sorry, but we basically we launched 1 month ago, so
Mhm.
we're still fixing bugs. But I will have a look
Okay.
in 1 or 2 days. This will be fixed. Thank you.
Okay. Thanks. No problem. So after you fix it, you can contact me with the links again, and I can share them with our community in Google Groups. No problem. Okay. Thanks for the presentation. Or is there anything else you wanted to present, or that's all for today? Yes. I will see what are the questions on the chat. There are just the questions about the links, so they will be provided later. So actually, I have one question because you showed Qiskit. How do you think how difficult it can be to integrate this tool with some other frameworks like Pendelane, or is it possible at all, or do you have it in plans, or it doesn't make sense?
Can you repeat that? Which tools? The second
Uh,
tool, the coding tool, or the
so
workflow?
for example, Pendelane. I believe that you heard about Pendelane from Xanadu.
Yeah, I know about Penlink, but you were asking about the coding
Yes,
platform or the workflow platform?
both. Let's say both, because
Yeah.
yeah. Mhm.
So for the coding, for the IDE, let's call it an IDE. We do have in plan to port also Circ and Penlink to it.
Okay,
Will
nice,
take. I mean, I cannot give you now a timeline, but probably by the end of the year we'll have Penny Lane.
nice.
There are so the platform is in a beta state. It does have some bugs. It's not fully perfect. We're still working on it. We're trying to make it as useful as possible, and we're trying to prioritize the features that will be most useful. And I think Penny Lane is one of the most useful features, and
Yes,
it's really high on
yes.
our.
That's why I ask about it. Yeah, because I know that Penlane is getting more and more popular. Uh, okay, good. Yeah. Do we have some questions from our audience? Maybe someone would like to unmute. So maybe I'll ask another question. So I understand that this is let's say an early stage, but can you maybe share with us your plans? Because I understand that this is already something like a startup. Can we call it a startup, or it's rather an academic project? Mhm.
No, it is a startup.
It
Yeah.
is a startup. Mhm.
Sorry. Yeah. So. Basically, we're trying to fill the needs of quantum researchers, let's say, and quantum professionals
Okay.
to see uh, what are the pain points when people are trying to build quantum application, especially software related. Because, yeah, we have big players working on the hardware. No, we cannot compete there. But yeah, in terms of software, we think we can do a really good job in filling out. I mean, addressing the pain points of students, let's say researchers, and mostly professionals, which work on getting real value out of quantum computers.
Okay. Yeah. So I can see a message from Arley that he can use the IDE platform even
Yeah.
without having the account, which is interesting. But anyway, he can try it and give you feedback, of course.
Yeah,
There's
you
another
can use
question.
you can
Yes.
sorry, Pavel, you can use the platform. You right now is you'll only need access you'll only need login if you need the AI assistant because for that you consume your own rate limits or models and all that. The platform you can use it. You will be, I mean, going forward, we're adding features like saving your code and coming back later to it. Then you'll need to be logged in. But yeah, we don't block usage for
Okay. All right.
unauthenticated.
There is a question from Ahmad. Do you have plans to upload its tutorials to YouTube? Or do you already have some tutorials?
We don't have tutorials yet on YouTube, but we do have plans to start a YouTube channel with
With tutorials.
tutorials on
Yeah.
this. Yeah,
I think you can also prepare some tutorials on the website as well. Yeah. Okay.
yeah,
Nice.
that's in plan.
Yeah. Good. Do we have some other questions from our participants?
If I can stop you for a moment,
Yes, please.
we we are looking. We believe both tools could be very useful for learning quantum computing, and we are looking for university research groups who are willing to use these tools. For
Okay.
example, using quantum flows can be very beneficial because you just create your workflows visually. You can run it, you can view the results, you can even download the code. And this would be, it's a very good way to learn about this, about quantum computing, about various things that you can do with a quantum computer. So we are actually looking for university professors who are teaching quantum computing course and would like to use these tools.
Okay, thanks. So actually, I'm not affiliated at the university, so I do not teach. But perhaps once the tool is more mature, perhaps Cured could try to use it in its workshops or courses. I know that we've already let's say briefly discussed it by email. So we'll see. Definitely, I think that would be great, as Radu said. Yeah, we have our. I think that we can try to contact our Q Education department at QWord. They're responsible for developing the educational materials and designing all the content of our workshop. So perhaps I believe they could be interested. Yeah, we'll see. Especially that yes, you are also part of Q Romania, so part of
Yeah,
QWord.
yeah,
Okay,
yeah. We
right.
actually have an event planned for November.
Uh-huh.
Yeah. And we'll plan to use these tools, and it will be the first event with up to 70 students, that's, I think, which will be using these tools, and
Oh, nice,
be
nice.
a good way to test it out in real life.
Yeah, this could be actually a good idea, right? To prepare the whole, let's say, curriculum for a workshop based on this tool, and then run a workshop similar to Q Bronze or Q Silver that are organized by QWord. Yeah. There's another question from Ahmad about fundings from National Science Center and plans for collaboration for research projects. Yeah, perhaps. So I think that definitely there are some opportunities some for international projects because I believe that the startup is already registered in Romania. Is that correct?
Yeah,
It's already
yeah,
registered, right? So it's a legal entity in Romania, but there are different opportunities for international collaboration, even like European Union funds. So there could be even more relevant, I believe. And so I can also tell you that QWord is currently collaborating with Cureka. Maybe you heard about Cureka. It's also let's say educational platform or they also run courses on quantum computing, and we work together with them in one European Union project funded by EAT. So I know that there could be such opportunities, so we can talk about it later. Yes, there is a comment from Maya. The work is really great, but please keep in mind to update Qiskit version to 2.2. Right now it is 1.4.4 and looking forward to see pendulum too. Yeah.
Yes, about that. The Qiskit version in IDE, it's 2.2, right? Sorry,
2.1.
2.1.
Yeah, so
Okay.
in the coding platform, in the IDE, it's 2.1 because that's the version we ported. We didn't port it 2.2 yet. But all the workflows, Radu, are
Yeah.
1.4, right?
Yeah, the workflows are running Qiskit 1.4.4. So there is a problem with we are using the Qiskit algorithms module, which was until I think until last month did not have support for Qiskit 2.2. Now it does, but it's still buggy. And for this reason, we are for the workflows platform, we are using 1.4.4 Qiskit. And actually, you will, if you will try to use the workflows using a Jupyter notebook using Qiskit 2.0 will not let you because there are some formatting issues and the way that how data is sent, and there is a difference between those versions. So for the moment, if you want to use workflows, you need Qiskit 1.4.4.
Okay, nice. Thank you. There is another question from Andrzej. Is there any development roadmap for this project, meaning which features are planned to be added in the near future?
Radu, you can go
Yeah.
with
Sorry, I mean, you can start.
Yeah, so we realized that these two, so we need to make these tools more working together. This is the long-term plan. They are a little bit separate. They're on different versions of Qiskit. They have different authorization, authentication types. We'll need to basically integrate them together more closely. But we also have some basic features, at least in the IDE, that need to be filled. The workflow is a little bit more mature. I think it can be used as is right now. For the IDE, there are basically features, like I said, like saving your workflows, having a history of your chats with the AI assistant. We want to build an MCP server that will help you research, maybe also index the articles from the archive or from different scientific journals, and you can have access to them on the topic that you're researching. But that's a little bit longer term. Yeah, but I guess feedback from your end is very important for us, and our roadmap is fluid and can be adapted to whatever people think it's useful. That's why feedback is
Great.
important.
Fantastic. Thanks, Sorin. There are also some other positive comments from Maya. Thank you so much for the explanations. Then we'll wait for the Qiskit to make a stable version. And a comment from Mohammad Reza. Decent visuals and hierarchical quantum chemistry algorithm structures. And yes, even more ideal via moving toward being platform agnostic in terms of SDKs. Thanks, Mohammad Reza. Good. Do we have more questions to our guests? Maybe someone would like to unmute and ask. Okay. If not, then let me thank our guests once again. So Radu, Sorin, thank you for the presentation. I will contact you later regarding the video recording to confirm its upload to YouTube. And yeah, we keep our fingers crossed for the development. So hopefully at some point in the future, we'll say that, wow, we are one of the first meetups that hosted this great platform. So yeah, there's a question about recording. The recording will be later uploaded to our YouTube channel. So you can find the profile of the Quantum AI Foundation on the YouTube channel.
Yeah.
Good.
Thank you, Pavel, for hosting us, and thank you for everyone for attending.
Thank you. I will now stop recording.